Yes, Mike Wright from Goddard, and this is, as Steve may have mentioned, kind of a subtask to the Moons of Mars team that Mike Earnhardt is leading. And so what I'm going to be talking about is what could we do from Phobos, assuming you had a Phobos base, what could be done on the surface of Mars, assuming that you've got some telerobotic rovers, a couple of telerobotic rovers that are equipped to conduct tasks in preparation for a human landing or for science. And so I'm going to be talking about that. So this is basically what we're going to be covering. So the concept description is as I mentioned, basically to take a look at, consider what tasks could be performed from Phobos on the surface of Mars, and how long that would take. At the time we started this, gosh, 2 or 3 years ago, we were looking at possible 500-day missions, and that's varies depending on the concepts that are being proposed at the time. I think Mike had mentioned the shorter missions as a possibility. But for the purposes of this study, we were looking at an extensive amount of time to do whatever could be possible. And we brainstormed on the possible tasks, including things like offloading landers, setting up infrastructure, that kind of thing. So we looked at those candidates that would be prime for this sort of thing. I've got a different pointer here. There we go. And it assumes a comm latency of less than 400 milliseconds, which is about the limit on what would make sense for a low latency situation when you're talking about controlling things from remotely. And we assumed that most tasks assumed are non-autonomous and non-high latency. And it includes pre-crewed missions, deployed surface assets, the power systems, the science labs, the logistics, whatever you could do to make to accomplish to make it easier for the crew once they get there. If there's something you can do ahead of time that would not use up the limited time that the crew is going to have on the surface of Mars, then it would be worth looking at, worth considering. We took the one case one for the 27-ton lander, and just as an example, because it had a significant capability of delivering assets to the surface and other capabilities like hoists and things like that. And we also looked at the analysis of the activities and the tasks themselves, looking at what value, what priority they would have with regards to what value they'd bring to the campaign, and also latency sensitivity, criticality, that kind of thing. And we did an assessment of those as well. This is basically just a flow chart. I'm not going to go through it, but it talks about how we developed the task lists and did the analysis and the feedback loops and inputs from various teams and that kind of thing. If these slides are posted for your access, feel free to contact me later and we can talk about that. Some of the general assumptions is that the assets are already deployed on the surface and equipped for low latency telerobotics, and with all the tools, all the equipment needed for that. I'm not going to read all this, but basically facilitating the operation of it from Phobos. And I'll talk a little about the reason why we looked at the Phobos situation too. Controlling monitoring of surface assets by orbiting crew. Minimum of 2 crew members, 1 for each rover, and we're looking at 4 crew proposed because we're talking about round-the-clock operations. And just as an aside, I know Mike had mentioned 6 hours for a 6-day mission. This is a lot more extensive than that. We're looking at doing it round the clock for as long as you could possibly do, 500-day mission, that kind of thing. Okay. So for the timeline assumptions, and when I developed the timelines for these tasks, and here I have a larger version of this later, but we took the Phobos base because that's what we were focusing on for the Moons of Mars team, and it also made sense from a loss of signal standpoint, assuming no orbiter comm relay. So we're looking at a worst case comm situation here, and when you see LOS, that's loss of signal, not line of sight in this presentation. And it gave us about the loss of signal lasted almost 7 hours. So you ended up with a 4.2-hour comm duration to accomplish something, and then you either stood down for 7 hours or you had some autonomous operations that you could do in the background. ISRU, for example, is a good example of there was a lot of autonomy associated with ISRU operations that could be done. And then when you get your comm back, see how things are going, take advantage of the time to manipulate or conduct operations, whatever you needed to do, and then go back into LOS. The bottom line from all this study is that we're really pointing toward the need for an orbiting relay. I mean, if you really want to take advantage of your time, you need like a Mars Tetris kind of a thing. And then we based our estimated task durations on a variety of different things, including some of the HST servicing missions, some of the robotic missions that the servicing missions that are being tested on station, and also we included some overhead time because things never go as planned anyway, and that we wanted to be as realistic as possible. And some of the studies from Terry Fong and some of the other folks indicated almost a third of your time could be just response time, writing down logs, getting preparation together, and waiting. So we took that into account as well. Some of the surface ops that we include, I'm not going to read all this, but basically, as I mentioned, logistics, setup, connections, and a lot of the science, which I'm going to focus on in detail later. This is just one example of something on the order of 60 timelines that we came up with for various tests, and it shows that you've got this 4.25 hour comm time, and then you've got an LOS. In this case, you've got some LiDAR, a laser survey going on autonomously, and then you take a look at your data, and you do some manipulator operations, some science stuff, and then you're back into LOS again. And this happens to be takes 2.5 shifts for each sample site for your outpost hazard site assessment. This particular task involved looking at potential landing sites and seeing if they were going to be safe for crew and for lander operations. This is an example of the ISRU production timeline. This is 5 shifts, almost 5 shifts, a little over 4. And you could see during the LOS periods, although you can't read any of that, there's a lot of stuff going on because it's one of those things. I put this up here because it's one that really takes advantage of your autonomous operations and in concert with the telerobotics operations as well. So it's a lot of choreography there associated with that. So one of the things that we looked at Goddard, Jake Bleacher and me and Mark Lupacell and some others were looking at a 2 science rover operation, what could be done with low latency telerobotics, and some notional traverses for those. So in this situation, we've got a Recon rover that gathers preliminary site data, and then a slower sampling rover that takes those sites that the Recon rover says, yeah, this is a really good place to go and take a sample. And then the slower sampling rover that's got more instruments on it goes and takes the sample. And in this scenario, we use both LT and possible HLT for working as you would, with MSL, for example. And as I mentioned before, 4 crews assumed for this: a science op lead and 2 a Recon rover op, sampling rover op lead, and the Phobos base operations, the housekeeping kind of stuff. Now that, of course, won't allow you to do around-the-clock operations. Looks like my thing's going down there. Let me try this one. That'll cut down on some of your around-the-clock operations, but you use what you can. The focus of the research is determine if life ever existed on Mars. So this is just the concept of the science investigation being conducted. And then we took a kind of a a guess at what would be some of the best instruments to include on each rover. And this is still being worked. We assume there would be LiDAR and surface samples at outcrops and core sampling being done. And there's no presumption that the crew would return to that, but could. I'm not going to read all this since we're low on time, but the Recon rover capabilities are here, auto nav, imaging, whatever it would take to assess a site for possible sample acquisition. And then the sampling rover capabilities has some more detailed instruments, GCMS. There's been a suggestion to put a grinder like a rat or something on it to clean the surface of the rock so you can get to it and do a little more analysis. Sign of life SOL detector, I call it, for determining whether there's a possibility of life. And this is another sample timeline that shows the sample acquisition. And in this situation, because it's so critical that that's one of those things that you really don't want to leave to autonomy necessarily, although a lot can happen in 20 years or 10 years as far as autonomous operations, robotic operations. But we felt that because the sample is so critical, you'd really want to use this via LLT versus relegate it to autonomy or HLT. So there's a lot of LOS here, and it takes some amount of time. In this situation, it takes 9 shifts to get to the point where you're doing sample analysis. I looked at this Centauri Montes. We did there's obviously a variety of places you could investigate, but we looked at the HEMSAG report where they isolated one particular area, and this shows where that area is, and there's a reason for it. There's some looks like flowing water at that area, and we looked at specific traverses for an LLT rover on and also footpaths. We call them footpaths for little side excursions where the sampling rover would actually go and take samples at those locations. It takes some amount of time. This is the Recon rover timeline. We just took a guess at a 500-meter traverse across that, and then that would take 3 hours based on the instruments that we selected and the amount of time it would take. This bottom line is crew operations, and this lists all the instruments that we considered for this particular rover, the Recon rover. For the sampling rover, that follows the Recon rover after that, all the considerations associated with that, and I came up with this timeline. This is quite longer. This is 10 hours per stop for the sampling rover. And the reason it took so long was because primarily the GCMS took some amount of time, and then also the rockabrador took quite amount of time to get its job done. So that ended up with a minimum of 10 hours. And then it goes on to the next site. Obviously not as many sites as the Recon rover had to check, but it's a lot slower, and it's going to the key sites. The footpath routes are shown here, where you've got you set up a geophysics station, and then the sampling rover takes the little route, and the Recon rover continues on, and then this is where the sampling rover, more detail on that, and these are MOLA images for those particular areas. And the timeline's repeated that I showed before for the 100 science sites that we could do, and the total round trip along one of those footpaths is 42 days based on the speed that we assumed. So regarding science, it's understood that this can all be complex, and that things like a backroom science support on Earth can be of help to the local crew operating the instruments. And one of the issues, some of the issues we came up with, the core drilling is obviously tedious. I think Chris Zachney is going to talk more about the instruments associated with drilling later in the week. Some of the maintenance is going to be a problem. Consumables are limited, similar to Sam on MSL. You've got a limited amount of consumables to do sample analysis, and so you have to be judicious about exactly what your how many stops you make and how many samples you take. And we talked about the instrument complement being still, it's a challenge to define it because, you've got a limited amount of mass, the speed, the cost, et cetera. I'm going to just briefly a couple of slides on how we have done some of the assessments. We looked at the various tasks and kind of tried to do a somewhat subjective assessment of quantifying which tasks would be better candidates for LLT and not. I mentioned the fact that the science samples are going to be higher because they're more critical. We looked at duration comparisons of the various surface tasks. As you can see, it takes quite long. This is hours, and none of these fit in that 36-hour window that Mike mentioned, but they could fit in a 500-soul mission if that is eventually decided upon. We could do quite a bit in that time in preparation for human landing. We did a value assessment. This is based on Steve Chappelle's work with the Kepner-Trigo decision-making process, basically an ranking assignment of relative weights to particular tasks. And this is some of what was resulted, including the lander offloading, some of the sample work and all. And it basically is a more quantitative way of assessing the value of a particular task with regards to LLT. And this is an example of the value assessment for the science tasks. Okay, so there are a lot of challenges associated with this with regards to time. And again, that can be mitigated through continuous comm coverage. Also, the support for the crew support. Obviously, they're going to have other things going on. Housekeeping operations, little things like sleep, eating, that kind of thing that takes up time that will mean you can't have a 24/7 operation necessarily. And the more mechanisms that you have for autonomy and telerobotics requires more mass and energy. But of course, by doing that, you offset it by having to have fewer environmental control stuff if you're reducing crew time on the surface. We've learned a lot, as Mike mentioned, about from terrestrial robotics and telerobotics, and the value of the assets on Mars make their functionality and longevity imperative, which is true of any mission that's going to be critical and one of a kind too. And there are a lot of common tasks that can be candidates for autonomy or supervised autonomy with contingency real-time intervention that the LLT affords for this. And lunar demonstration, of course, could be beneficial to long-term Mars mission planning, as is the ISS testing that has been done with this as well. Potential benefits, it enables pre-landing operations by crew in Mars system or post-departure by operators on Earth of tasks on the surface, and it affords control and monitoring of critical operations, including the science, and it can help mitigate environmental and planetary protection concerns. You don't have the crew on the surface, you can do what you need to do to mitigate those issues in special regions. And unexpected contingencies suggests the need for direct human interaction that is afforded by the LLT. And those are the people that have helped with this effort as well. And I guess we have time for questions, maybe? Okay. Thank you.
There's time for one question.
And we'd invite discussion of this later in the week if you're all going to be here for the survey conference to talk more detail about instruments and operations for this. Yes?
Do we have a rough feeling at this point of what we should expect in terms of the amount of housekeeping activity that will be required with the systems we envision, right, like that, like in terms of hours of housekeeping time per hour of rover driver on the surface, or
right.
researcher in orbit?
We haven't looked at that. If ISS is any example, it's going to be a pretty large percentage. Maybe Mike has a better idea of that.
I could imagine it being very different too.
It'd be interesting.
What's the fraction of the time necessary by the people in orbit? How much time do they have to spend on housekeeping versus doing telerobotic work?
I had that in our command line.
Yeah.
It's about 20% of the time.
Oh, and how does that compare to ISS? Is it a lot better? It's similar? That's what I was hoping. All right, cool, all right.
Your Nemo work and some of the other demos, have they also demonstrated a comparable amount of time for housekeeping? It's different. It's different, yeah, it's a different situation. Okay. Thank you.
All right, thank you, everyone. We're going to have a break now. We'll go until 10 minutes. We'll get back here just before